As a data scientist, one thing you'll need to get familiar with is machine learning. But just what exactly is machine learning? Well, first off, machine learning is the process of having a machine, like a computer, learn something from some sort of data set through the use of various algorithms. But how is that different than running some data through a spreadsheet? Well, machine learning also has the capability of self-improvement. In other words, as each new piece of data is processed, more can be learned about the dataset. So with machine learning, each new piece of data actually helps to improve the analysis of the entire dataset. Put another way, machine learning gains experience from the data that it encounters and is able to make better judgments along the way. Now, machine learning is 100% a method of data science. It's a tool created, managed, and used by data scientists to analyze data and collect useful information. Or at least you hope it's useful. You'd be surprised how much information we have today that is collected through the process of machine learning. But machines and people don't intuitively know things. You have to train them. And the only way to do that with machine learning is to provide training data. Imagine you wanted to determine if a patient is diabetic. Well, you'd need a lot of information on the patients that have and don't have diabetes in order to be able to make that determination in the future. And that's the training data. Now, with machine learning, we can explore data more holistically with tons of training behind it. And that enables us to make more informed decisions. If we've used machine learning to explore billions of pieces of data to arrive at a high probability conclusion, like you're diabetic, then we can make decisions based on that information with higher confidence. A good example of that is how we've made apps and devices far more intuitive. We've been able to explore how users interact with devices and apps, what they do under certain conditions, and so on. And we've been able to improve the systems we interact with accordingly. For example, lots of browsers will actually predict what you're going to do next and then preload the next web page for you. That way, when you click to go to the next page, it's actually already loaded and the performance will seem lightning quick. Now, there are lots of types of machine learning out there. A data scientist will have to implement the type that makes the most sense for the specific situation at hand. Now, there's traditional machine learning, and basically that's when algorithms learn from the data, but where the choice of algorithms and input data is made by subject matter experts. Traditional ML expects all data to be in structured formats. There's also deep learning. Now, put simply, deep learning is effectively an implementation based on neural networks. It also generally sits on top of other machine learning algorithms. Now, one of the most common types of machine learning is supervised machine learning. Now, supervised machine learning means training models based on data that you know the answer to already. So again, if we wanted to train a model to predict whether a patient is diabetic, we'd first need to train the model to identify the characteristics of someone that we know is diabetic. And that would mean feeding data into the model where we already know the correct answers and the data associated to it. Meanwhile, there's unsupervised machine learning. Now, with unsupervised machine learning, we don't actually know the answer. We're feeding the data into a model and trying to figure out what it means. For example, imagine I had a giant cluster of something like penguins, and I wanted to classify them in some way, but I just don't know what classification it should be. Well, I could use unsupervised machine learning to ask that the penguins be split up into 3 logical groups. Then I can explore the resulting data to see what different ways I could organize those penguins. Now, when we're implementing machine learning, the tasks you'll perform are generally always the same. The first thing you'll do is train the model. You'll provide an input dataset and you'll train the model to produce the outcome you want. Now, that could be predicting the price of a car, predicting whether a patient is diabetic, grouping penguins into logical clusters, and so on. Now, once you have a model that's been trained to produce an answer that you like, you can then deploy the model. Now, that means making it available to other consumers. You can deploy the model as a web service or even onto an edge device for more immediate data analysis. Now, technically speaking, with Azure, you can train and deploy models automatically, and this will help you to tune your parameters and algorithms more efficiently too. Now, regardless of how you create your model, you'll then need to manage it, and that can mean testing, tweaking parameters, adding more training data, and so on. You could also adjust permissions as to who can even access the deployed model. And of course, you'll track your model. You'll want to know how it's performing in terms of producing useful answers. With each new piece of data, there's a potential opportunity to improve the model. Now, when we deploy a model, we call it a machine learning service. Now, one common machine learning service that's been built and deployed by Microsoft is anomaly detection. Now, the purpose of anomaly detection is to inspect data and detect outliers. So imagine you have data that typically sits between 0 and 1, but then you suddenly get a spike at 100. Well, that's clearly an anomaly, right? Well, what if the data is trending upwards and then that spike happens? What if the data is typically quite noisy? There are lots of situations where just looking at the chart doesn't clearly identify the anomaly. Well, with anomaly detection, the context of the entire dataset is analyzed to determine if an individual data point is actually an issue. Now, anomaly detection is really useful for performing root cause analysis on your data. It helps us to detect issues in our datasets. Now, with enough training, the problems that happen as a result of these anomalies can be mitigated through earlier detection. Now, another Microsoft machine learning service is computer vision. Now, with computer vision, we can detect and label objects in pictures and videos. So imagine you had a random picture of, say, a crowd of people outside. Well, with computer vision, you can analyze that picture and come up with a description like a crowd of people at an outside concert. Or you can identify objects in the picture like trees and people, food, brands, and so on. You can even identify individual faces or people. Now, computer vision works by recognizing patterns in images. Now, Microsoft has already trained their models to recognize certain very common things, like faces and brands and everyday objects. But you can train your own model to recognize objects that matter to your specific situation. Basically, the main idea of computer vision is to imitate human vision. In fact, one of the primary use cases for computer vision is to be able to describe the visual world to someone without sight. Now, one last example of a Microsoft machine learning service is natural language processing, or NLP. Now, NLP lets you analyze languages, not just text, but whole language. So that can mean finding characters, including hieroglyphs, finding words, and finding sentences. NLP can find those things by scanning documents or even pictures. But it's not just about regurgitating and detecting text. It's also about understanding the language it finds. With NLP, you can detect the actual meaning behind what's been written. And best of all, NLP can generate language too. So that means producing text for users to consume based on intent. A prime example of that would be an automated support bot on a service website. When it comes to machine learning, one of the most important things you can have, if not the most important thing, is datasets. So what's a dataset? Well, a dataset is effectively just a collection of data. It's that simple. All that matters is that the data in the dataset has meaning to your machine learning activity. Now, the source of that dataset can be just about anything. The most common is obviously database tables, and in fact, that's likely where you're going to get most of your data too. But it can also be a file repository, blob storage, and so on. The data itself can be pretty wide-ranging too. It doesn't just have to be tabular data that you get from a standard database table. It can be documents or files. For example, imagine you wanted to identify a set of images to determine what sort of animal is in each image. Well, that's obviously image files then, right? Well, it's still data. Now, at the end of the day, it's imperative that your data is of high quality. After all, your models are only going to be as good as your data. Garbage in, garbage out, right? Now, imagine your standard supervised and unsupervised machine learning models. In a supervised machine learning scenario, you're training your model on how to make predictions based on answers that you've already given it. So you want your data to be reflective of that. If you were trying to predict the price of a car, and all you gave it for data was the color of the upholstery, you're not going to get a good model. And it's worse for unsupervised learning where you can't feed the answer to the model. Your data has to be high quality. Now, of course, that's not easy. One of the reasons to create these machine learning services is so that you can determine answers to questions based on limited information. So creating a perfect dataset that can be used to create good models can be very difficult and time-consuming. And anything that's time-consuming is expensive too. And if you're going to bring real people into the mix to help cleanse and label the training data, then that can be even more expensive. Now, when you embark on your machine learning journey, you'll typically use your datasets in one of two ways. Now, the first will be to actually transform the raw data. Now, you may have your data set in a very easy to understand and workable state. For example, imagine a data set of cars that has all sorts of information like miles per gallon and horsepower. Now, anyone providing you that data for your data set will easily be able to do so, but the model might need the data slightly differently. For example, for MPG and horsepower, you might want to make sure that those two values are normalized to the same scale so that the model doesn't get any bias introduced from the bigger number. Now, that normalization is a transformation, and you'll do that a lot. And then, of course, the main thing that you'll do with your dataset is actually use it to make predictions and gain insights on your model. Okay, so that's what you'll use a dataset for, but how do you manage your datasets? Well, the first thing you want to do is maintain a single copy. There should be a single canonical version of your dataset somewhere that everyone agrees is the master copy. And once you've established that central location and canonical copy, then the next thing you need to do is give persistent access to that dataset. Whoever it is that needs access to that data should absolutely be able to do so. There might be loads of models being trained, or maybe there's just a need to explore that dataset manually for insights. Regardless, whoever needs to see that data should be able to do so whenever they need to. Now, why? Well, because at the end of the day, we're trying to build usable and useful models for the community or for our customers. And that means that everyone involved should be able to collaborate and share. Any insights, thoughts, or ideas that people have along the way will be useful. And that means that we must allow people to interact with the actual central dataset. Now, once people or services can access the dataset, they're going to want to manipulate that dataset. And there's lots of ways that generally happens. One common strategy is actually to combine datasets. So if you had a database of diabetes patients, it might be useful to combine that dataset with a database of high blood pressure patients and see if there's any correlation there. Or maybe you're attempting to predict something that simply requires data from multiple datasets. Now, another manipulation strategy is to create categories for grouping, and that means taking the root dataset and categorizing the data prior to using it. Now, I mentioned earlier that datasets are often transformed before use. Well, one of the most common ways to do that is to modify columns of data, and that means changing the scale of data, removing or renaming columns, or a whole host of other things. And a last example would be dealing with missing values. Sometimes you get a dataset that simply has holes in it. So what do you do when there's missing data? Do you ignore the row completely, or do you fill in the holes based on other criteria? So let's go over a few examples of some standard dataset manipulation tasks that you can use against your dataset. Now first, once you have a dataset, you can use it to generate a whole host of statistics. Now depending on the toolset that you're using, some of those statistics can be generated for you. For example, with Azure ML Studio, you can explore a dataset and you can obviously see how many rows and columns it has. But you can also see statistical information about each individual column too. And of course, having data means that you can apply calculations to it. So you don't have to be satisfied with built-in statistics. You can use whatever tool you want to explore the data, apply some calculations, and then collect whatever insights you want from it. And that can even go so far as to allow you to write your own custom code to play with your dataset. But likely one of the most common manipulation tasks is to normalize the data. Now imagine you have a bunch of different columns and each column of data is in a wildly different scale than the others. And importantly, let's say that you believe these columns of data should share equal importance. In other words, you don't want any of these columns to have more or less bias in the model than the other columns. Now with normalization, each of these columns are brought into the same scale and magnitude. Or you can just outright scale the values. Now scaling is different from normalizing because it just brings the data to the same scale. Normalization is more radical than that because it works to give the values the same numerical meaning. Now you can also analyze your dataset and place certain values into, say, bins. Now, for example, imagine quartiles or histograms. In those cases, you're looking at data and deciding which bucket it belongs to simply based on its value compared to the entire range of data. Then you can play with the individual buckets in isolation of the other buckets. Well, you can do the same thing when manipulating your dataset. Now, one thing I do all the time is divide my dataset into training and testing sets. So if I want to use my dataset to train a model, how am I going to score that model? I'd need another dataset that also has the right answers in it so that I can run the model against a second dataset and compare the answers. Well, if one dataset is expensive to have, then two is even more expensive. Twice as expensive, actually. But what I can do is I can split my dataset into two parts. One part to train the model, and the other part to test it. And finally, you can apply a sampling methodology. Rather than using the entire dataset in the training process, you can sample some of the data from the dataset to be used. To this point in the course, we've come to understand the importance of datasets in machine learning. But what are they really? Well, at the end of the day, a dataset is really just a mechanism of organizing information. A dataset offers us the ability to explore, navigate, and understand the data contained within it. If we think about tabular data versus, say, a file share, then individual rows in a dataset represent what's called a data point. Sometimes people confuse an individual value, like a number, as being a data point. But in the context of machine learning, it's the entire row that's considered the data point. Meanwhile, each of the columns in the dataset represent, or sometimes represent, what we call features of the data. So for example, I could have a dataset of cars. Now each car would be a data point in the dataset, but each characteristic of the car, like miles per gallon, would be considered a feature of the data. Now when we start using a dataset for the purpose of machine learning, there are two types that are worth noting. First is what we call raw data, and raw data is considered unlabeled. Meanwhile, the second type of data is the opposite, labeled data. Now, labeled data means that we've analyzed the data and given the answers that we're looking for when we go about training a model. So, for example, imagine we're training a model to tell if a patient is diabetic. Our dataset would contain a bunch of patients in it. Well, any patient that includes the information that says whether the patient is diabetic is considered labeled data, whereas any data point in the dataset that does not have the information that says whether the patient is diabetic is considered unlabeled. So let's dive into these a little bit. First, let's talk about unlabeled data. Now, unlabeled data is our initial raw dataset that we pull from various sources. Now, getting raw data is generally pretty easy. It represents all of the peripheral information that you can get from lots of different sources. So if we think of our patient list, that's pretty readily available, isn't it? Lots of different databases are gonna have that data. But importantly, an unlabeled dataset has no features. Well, it certainly contains columns of information in the dataset, but the more appropriate description is that the column doesn't quite have meaning yet. That's why feature is a good word. It means that we have a useful value associated to our data points. Then there's labeled data. For data to be considered labeled, it needs to have been tagged with at least one label. Probably the best example I could give you for this would be a dataset that contains tons of pictures of something like fruit. Now, each picture would include a label that tells us what kind of fruit is in the picture. An apple, a banana, or an orange, for example. Now, adding a label means adding meaning to the data. It tells us what the data point is, or at least what it means. So saying the picture is an orange, or the patient is diabetic, or a car costs $20,000 means that we've labeled the data. We've given an answer. Now, unfortunately, labeling data generally requires human interpretation. We need a person to tell us what that data means. And only once we have that data can we train a model to start figuring that out on its own. But of course, the more complex the dataset, the more expensive it is to have a human label it. So generally speaking, a labeled dataset is quite a bit more expensive and difficult to get than a raw, unlabeled dataset. Now, there are lots of labels that we're already pretty familiar with today, even if we didn't previously think of them as labels. For example, think of a photograph. Anytime you see a picture, it contains something. A person, a horse, a plane, or even an event of some kind. The picture itself can be described in some way, and that's a label. But it doesn't just have to be a thing. You can analyze things like emails, online reviews, or even social media posts for things like tone. The tone of that post can then be its label. For example, imagine a set of hotel reviews online. Maybe there are thousands of reviews. Well, with machine learning, you could analyze each of the reviews and then give an overall score to the hotel based on the average tone of all of the reviews. And one more label type example would be something like activity in a video. What the subjects are doing can be the label. So imagine reviewing a bunch of videos and noting the general activity of the subjects in the video. Now you'd be able to pick out abnormal behaviors by doing that, wouldn't you? So what's the deal with labeling anyway? How is it useful to machine learning? Well, when we talk about supervised machine learning, the models that we're trying to train need to have labeled data applied to them in order to learn how to make accurate predictions. In other words, supervised machine learning needs pre-labeled data in order to be trained. Meanwhile, with unsupervised machine learning, where we have no labeled data, the models are trained to predict outcomes from the data. In other words, unsupervised machine learning doesn't use labeled data and tries to derive meaning from the data. When we explore data sets that we use for modeling, we sometimes refer to their features. But just what is a feature? Well, first and foremost, a feature represents meaningful data, and meaning will be different for different models. For example, if you are trying to predict the price of a car, the upholstery color probably isn't meaningful, but horsepower would be meaningful. Sometimes features are referred to as attributes, and those terms are interchangeable, but generally the most correct term is feature. At any rate, what makes a feature is that it can be analyzed. The objective of the model is to read the feature's data and then use the intended meaning behind that data to derive whatever conclusion it's trying to get. And features can be just about anything. They can be very diverse. A single dataset may have lots of different features, and some features may have more weight than others. Now, put as simply as possible, a feature in a dataset contains useful information about the data in that dataset. It's easiest to think of a dataset as tabular, and that means that each thing that we're analyzing is a row, and the features are stored as columns. But it's important to remember that all features are columns, but not all columns are features. And columns are also sometimes referred to as fields. So here we have a ton of different names for almost the same thing: fields, columns, attributes, and features. Now those terms can be used more or less interchangeably, but again, the most accurate to use term is feature. So just how do features fit into the whole machine learning process? Well, features are the lifeblood of a good model, and that means that machine learning includes a whole sub-process of feature engineering. Well, what the heck is that? Well, the first thing is to imagine the data that you have. Let's pretend that your goal is to be able to determine whether patients are diabetic. Well, to do that, you need to collect a whole ton of data about patients. But once you have all that data, you need to figure out what the features of that data are. Whether someone enjoys playing with Pokemon cards is likely inconsequential to whether they're diabetic, so you can remove or ignore that data. Meanwhile, if someone has high blood pressure, that might be a useful piece of data, so you'd keep that as a feature of your dataset. Now, those features ultimately feed into your model. Whether it's supervised or unsupervised learning, features mean that you know that you're feeding in meaningful data into your model to achieve the outcome that you're looking for. And ultimately, the output of your model allows you to potentially take meaningful insights from your original input data. But let's not beat about the bush here. Having data is good, having features is good, but if your data isn't of quality, you're gonna have a bad time. In computer science, a common phrase is garbage in, garbage out. In other words, if you're feeding low quality data into your model, you can expect low quality results. Poor quality data will have a negative impact on your machine learning predictions, full stop. For example, imagine you wanted to predict whether a patient was diabetic. That's important, right? Well, if your input data is poor quality, how could you ever trust those results? More than that, your insights would be compromised too. We're not just talking about the results of your model, but also the insights that you gain from those results. If your model results are questionable by themselves, then any insights that you can potentially gain from those results are even more questionable. Now, it's also important to remember that it's not just the data that can be poor quality. Business goals can have poor quality as well, and those can differ based on need. Now, data modeling and feature engineering is hard, so having a business that's not so clear on the goals and objectives of the model that you're building isn't guaranteed to lead to something useful. I mean, It might, but that would be by accident. So everyone needs to be clear on the business goals. Now, I've mentioned feature engineering a couple of times here. Now, that might seem pretty intuitive to you at this point, but let's quickly go over what I meant by that. First, feature engineering means employing your domain knowledge on the data that you have. Remember, features need to be meaningful, but only someone with domain expertise can tell you whether a particular piece of data has meaning. So the purpose of feature engineering is to look at a raw dataset and extract the features from the dataset, or at least identify the features in that dataset. Now, if you can implement feature engineering well, then you'll find that you drastically improve the predictions made by your model. Okay, so just how exactly do you prepare features? Well, there are a ton of different strategies that you can use to do that. For example, one way is what's called extraction. The idea here is to take a raw dataset and extract the data that you want from that dataset into a new dataset. So imagine you wanted to predict the price of a car. Then you're presented with a raw dataset that contains tons of information about cars. Well, as a domain expert, you'd analyze that dataset and identify which columns of information actually have meaning to the objective of predicting the price of a car. So horsepower, yes; upholstery color, no. So you'd extract the horsepower column. Now, another strategy is transformation. Now, that means taking the raw dataset and transforming it into something else. Now, that can include adjusting the scale of some of the columns, removing bad rows, or even normalizing some data. The objective is to augment the raw data into something else that can be fed into a model. And lastly, there's selection. Now, selection is effectively the opposite of extraction. With extraction, we extract the columns of data that we want. With selection, we remove the columns that we don't want. So going back to the example of a dataset of cars where we had horsepower and upholstery color, rather than extracting the horsepower, we drop the upholstery color. It's the same result, just a different style. Now, whether you're selecting, enhancing, or engineering your features, there are a few best practices that you should follow. For example, definitely work with subject matter experts, or SMEs. SMEs are the domain experts. They know how the data values work together. We can all more or less wrap our heads around patient data, but most of us aren't doctors. So if we're trying to create a data set that we'll use to predict whether patients are diabetic, it's probably best to involve an SME like a doctor in selecting our features. And we should definitely focus on our objectives. If the goal is to predict diabetes, that's very different than predicting cancer. If we're trying to determine meaning from the data versus a prediction, then that's also very different. Knowing what we're trying to do with the data will greatly affect how we're going to engineer our features. Also, it's important to understand the relationships between data. Sometimes individual features make no sense without other features for context. For example, in oil and gas, pressure, temperature, and volume are all tightly related to each other in the context of a well. Now, having one value but not the other two could greatly impact whether the model can even be run, never mind the usefulness of the output. It's also ideal that you use the datasets that you create to train several models. Modeling is not deterministic. In other words, models work based on probability. So each time you run your model, you will get slightly different results. And that's fine. Run it repeatedly and through different models and algorithms to see what insights you can get. And you should train continuously. Updated data, updated algorithms, and even different models altogether can all play a role in what sort of insights you get. So each time you run the model, especially if you've got new data to work with, can lead to some more interesting results. And finally, simplicity is key. Your data should be as easy to understand as possible. So you should work to continuously reduce complexity in your data. For example, I've had people that love to put little fudge factors into their dataset. Now, I understand why. It results in some better data on the other side. But having fudge factors that no one else understands can only lead to confusion down the road. With respect to machine learning algorithms, it really boils down to three main categories: regression, classification, and clustering. So let's take a moment to talk about regression algorithms. First of all, what is a regression algorithm? Well, regression analysis is a type of predictive modeling. Now, what that means is that it attempts to calculate the relationships or correlation between dependent and independent variables. In other words, how do all these features relate to each other and to the desired prediction? For example, imagine I wanted to predict the price of a car. Well, I might have a data set that includes a whole bunch of information about cars. But how does all that information correlate to the price? Well, that's what a regression model attempts to answer. Now, there are lots of use cases for regression algorithms. For example, you can use a regression algorithm to perform forecasting. Now, put overly simplistically, a regression model is about taking information and producing a numerical output. So, for example, I could use a regression model to take in a bunch of environmental data and then predict what the temperature is going to be like tomorrow. Now, regression algorithms are particularly good for identifying causal relationships between data as well. For example, imagine you actually were building a model that could predict tomorrow's temperature. Well, obviously, you'd want to train that model with known data from the past. Well, you might find during the training process that there are certain environmental factors that play a much more direct role in the temperature than you previously thought. Now, of course, we understand the weather pretty well by now, so it'd be pretty unlikely that we'd find something new, but that's just an example. Your data might produce some interesting correlations that you hadn't realized before. And since regression is about analyzing data for numeric responses, it also means that it's particularly good for time series modeling. You'll find that the process industry uses regression quite a lot. So, what are the benefits of regression algorithms? Why use that versus other types of models? Well, we've already gone over one of the primary benefits of regression algorithms, and that's the ability to analyze the relationships and correlation between data. In fact, one of the best benefits of the regression algorithm is the ability to identify the effect of independent variables. Now imagine that scenario of predicting the price of a car. Now imagine that a single variable is tweaked, like let's say stroke, and then you notice a stark impact on the predicted price of the car. Well, that would be interesting, wouldn't it? It gives you some insight into the impact of the importance of some of your features. And naturally, regression lets you compare the effects of scaling on your data. Sometimes the very scale of your data can play a huge role in your outcome. And while that might be meaningful, it can also tell you that you need to transform your dataset in order to get improved outcomes. Now, we say regression as a catch-all term, but there's actually lots of different kinds of regression algorithms. Probably the most common is linear regression. Linear regression allows the model to determine the relationship between dependent and independent variables. For clarity, a dependent variable is continuous, but an independent variable doesn't have to be. It can be continuous or discrete. Continuous means that the value can be continuously measured. So think of a flow of water. It can be flowing a lot, or not at all, or somewhere in between. And no matter when you measure it, the value can be different. Meanwhile, a discrete variable has a specific state. So think of a light switch. It can be on or it can be off, but it can't be anything else. So no matter when you measure it, it's gonna be one of those states. Now the point of linear regression is to determine the line of best fit between your data to produce an appropriate outcome. Now, when you trained the model, you trained it with known answers. So the linear regression algorithm drew a line of best fit between the data in your dataset that led to the value that was closest to the answer that you gave it. Now that line of best fit is then used to make future predictions. Another type of regression is logistic regression. Logistic regression is used to determine the success or failure of an event. Basically, the outcome is, or the dependent variable is, binary. What this means is that logistic regression can actually be much more useful for classification models than for regression models. They just happen to use the same strategy in this case. Next, we have polynomial regression. Now, polynomial regression is a regression equation. Basically, a regression analysis is considered a polynomial regression analysis if the analysis between the independent variables and the dependent variables are modeled to an nth degree. Then there's stepwise regression. Now, stepwise regression analysis is used in situations where there's multiple independent variables. In fact, stepwise analysis is generally used when you don't really know what the features of your dataset are. So what stepwise analysis does is that it selects your variables automatically. It can include and exclude variables using multiple independent runs of the model to determine the impact on the model output. If there's an insignificant impact on the output, the variable is ignored altogether. Now, another type of regression is ridge regression. Now, ridge regression is very useful when you have lots of highly correlated independent variables. Now, when you use regression strategies like linear regression, you can actually get added bias in your results. Well, one of the biggest benefits of ridge regression is that it reduces bias through the use of a shrinkage parameter. Now, ultimately, the result is that ridge regression can reduce the occurrence of errors in your output when you have lots of highly correlated independent variables. Next, we have lasso regression. The idea behind lasso is that it can help to reduce variability, and that makes it very similar to the ridge regression algorithm. But lasso also helps to improve the accuracy of linear models. So while it'll help reduce variability and bias, it will also be much more accurate. Now, under the hood, lasso works very similarly to ridge because it also penalizes the absolute size of coefficients. In other words, it uses the same type of fancy math. Now, effectively, it tends to use absolute values to make the various calculations. And finally, there's ElasticNet regression. ElasticNet attempts to be a hybrid of lasso and ridge regressions. Both lasso and ridge are very good algorithms, so ElasticNet attempts to take the best of both algorithms and combine it into one. So naturally, that means ElasticNet is primarily used when there are multiple correlated features. But the primary benefit of ElasticNet is that there's no limitation on variable selections. So you can select whatever or however many variables that you want, apply ElasticNet, and get a suitable outcome. Now, with respect to machine learning algorithms, again, it really boils down to those three main categories: regression, classification, and clustering. So let's take a moment to talk about classification algorithms. Now, first of all, what is a classification algorithm? Well, the main objective of a classification algorithm is to, well, classify things. Put another way, the idea is to obtain boundary conditions for the data. For classification algorithms, you need to identify the various target classes, or things, that it's going to be. Then you can run the model to predict which target class the data belongs to. Let's dive into this a little bit. Now, during this course, I've given the example of trying to determine if a patient is diabetic or not, and that's an example of classification. Obviously, there's lots of examples of what your target class could be, but it doesn't just have to be binary like that either. So one example would be, say, the classification of veggies based on their shape, color, or even taste. As a chef, or even a parent, it might be incredibly useful to search for the best veggies based on certain criteria for a particular meal, or even just a picky kid. Now, you could even use a classification model to predict consumer purchasing decisions. Now, for example, let's imagine a customer logs into a home improvement site and purchases some drywall. Well, a classification model could be used to determine what the most likely upsell would be. So you could give the customer links to likely items to purchase after the drywall, like drywall mud, drywall screws, putty knives, and so on. Classification can also be about certain criteria of the subject too. So while we can see a whole host of pictures about dogs, cats, fish, and other animals, a classification model can be used to organize and label the animals based on physical criteria, such as the shape of their snout, for example. I mean, that's effectively how we get the taxonomic tree of life. So how are dataset features used with classification models? Well, just like regression models, dataset features are also used to train classification models. In other words, it's still gonna be labeled data that you can use to train your model. By having the labels in your training data, you'll be able to train the model on how to define the boundary conditions for each data value. So imagine again our example of classifying dogs and cats based on their snout size. Well, while the snout size is the classification, boundary conditions would be things like the length or the girth of the snout. Now, since we're talking about classification models, it's best to make sure that we're clear on some of the terms that are generally used. First, there's the term classifier. A classifier is the actual algorithm that correlates the input data to the specific classification we want. A feature, as we said before, is a single measurable property of the thing we're trying to classify. So in our dogs and cats example, the snout length would be considered a feature. Then there's a multi-class classification. With multi-class classification, there are many possible outcomes, but this object can only be one of them. For example, an object can be a tomato, a banana, an orange, or an apple, but it couldn't possibly be all of them. There are many different kinds of fruit, but the object can only be one kind of fruit. So multi-class classification is about defining all these different classifications, but then choosing one of them. Now we talk a lot about classification models, but what's the formal definition? Well, a classification model is a model that predicts classification labels for a given set of input data. Binary classification is when the output is a dichotomy, meaning there can only be one of two possible outcomes. The light switch will either be on or off. The patient is diabetic or not. That's a binary classification. And finally, there's multi-label classification. It's important to understand that classification doesn't just have to be about giving a data point a single classification. Things can have many classifications. For example, a blog post can be about politics, a person, and a location all at the same time. Looking at a single object can lead to multiple classifications, and that's a multi-label classification. So what are some examples of classification algorithms? Well, the most obvious example is medical diagnosis. In fact, we've used that example quite a lot just in this course. A classification model can review patient data and then give a diagnosis based on that data. The patient could be diabetic, have Alzheimer's, or have a clean bill of health. You can also use a classification model to determine the meaning behind online posts. Now, for example, imagine a hotel with lots of online reviews. You can analyze each of the reviews and determine if their tone suggests that the review is positive or negative, and that would be a classification. Facial recognition is a form of classification too. You'd scan a face and attempt to identify the subject. That identification is a form of classification. And one last example would be spam detection. A classification model would implement binary classification to determine if the incoming message is spam or not. Now, classification algorithms are very similar to regression algorithms in that they review all of the input features. Where it differs is that the outcome is a discrete state versus a numeric continuous output. Nevertheless, one of the most common algorithms used is linear classifiers. This includes algorithms like logistic regression, the naive Bayes classifier, and Fisher's linear discriminant. Now, quadratic classifiers are similar to linear classifiers, except, to put it simply, they use squared sizes instead. There's not nearly enough time to go into the math on that, though. Neural networks is another common implementation. These can be very useful because it allows you to roll multiple different algorithms or even your own custom algorithms. And finally, and probably the most obviously, another method of classification is decision trees. And that makes intuitive sense, doesn't it? Review the data, make a decision. Review more data, another decision. Reach the end of the tree, there's your state. With respect to machine learning algorithm, again, it boils down to three main categories: regression, classification, and clustering. So let's take a moment to talk about clustering algorithms. So just what is a clustering algorithm? Well, a clustering algorithm, clusters objects together. Basically, it's a method of grouping objects in a dataset into clusters. And not just any cluster, of course. The clusters have to be meaningful in some way. The objects are clustered based on some sort of similarity. I tend to refer to this strategy as logical grouping. For example, imagine you had a set of vehicles, just a random cacophony of vehicles in a parking garage. Then you want to group that data into three logical clusters. Well, how do you do that? What's the basis of this organization? That's what clustering algorithms do for us. They help us figure out what that grouping methodology needs to be. Now, clustering algorithms work in a fairly simple way. First, and probably most obviously, objects in a cluster share similarities. What we don't know from the outset is what those similarities are. In our example of the random vehicles, we don't yet know what a good way of grouping the vehicles is. But once we have that grouping, then we'll know what the similarities are within those groups. Maybe it's color, maybe it's size. Now, one thing about clusters is that the objects in each of the different clusters are different. So if we were to group our vehicles by color, then we'd know that the vehicles in one cluster are most definitely a different color than the vehicles in another cluster. Now, mathematically, the clustering algorithms determine whether objects are similar based on their representative proximity to each other. So if we consider creating 3 logical groups of vehicles based on their color, you know there are more than 3 colors. So you could have a red cluster, a blue cluster, and a green cluster, and then colors that are close enough to particular clusters to be included in those clusters. But we can intuitively know what a good clustering strategy would be if we wanted to group vehicles into 3 logical groups. So let's consider this chart, for example. In this chart, our obvious clustering would be by weight and height. The result would have 3 clusters that seem to correspond quite nicely to the vehicle type: motorcycles, cars, and trucks. Now, when we chart the data by weight and height, we can see the obvious clusters. But if we charted the data based on color, it might be less obvious. And if we charted the data by number of wheels, we'd see 2 obvious clusters, but not necessarily the 3 that we're looking for. Now, ultimately, clustering algorithms are about arranging data in different ways until we can make out obvious groupings. Now, for clustering algorithms, there are 2 main methods involved. The first method is hierarchical. With the hierarchical method, each point is initially placed in its own cluster. Then, as each data point is explored, it's placed into the closest cluster. What that means is that as each new data point is added and the clusters grow or shift, individual points may actually move from one cluster to another. So in our vehicle example, we may have had a car and a truck that were in the same cluster to begin with, until we realized that they were quite different. So this is like exploring the data to see what the solution would be. Now, the other method is point assignment. In this method, we actually start with the clusters, and then each point is placed into the nearest cluster. So in our vehicle example, we could have started with possible clusters like vehicle type, and then each new vehicle that we examined, we just put into the correct cluster. So this is more like starting with a solution and seeing if the data fits. So let's review the different types of clustering. The first type is centroid-based clustering. With centroid-based clustering, we're dealing with non-hierarchical clusters. Basically, the idea is that all the data is organized into non-hierarchical clusters. An algorithm is generally used to figure out what the clusters actually are. Now, k-means is the most common algorithm used, but there are other types. And the centroid strategy is extremely efficient. However, the centroid-based clustering strategy is heavily reliant on starting conditions. Effectively, you've got to graph everything before you can figure out what the clusters could be. Another type of clustering is hierarchical clustering. Unsurprisingly, this is used for hierarchical datasets. Basically, the main idea is that all the data can be organized into a gigantic tree of clusters. So every single data point is effectively its own cluster. But then, any number of clusters can be selected. Then, once the number of clusters is selected, the tree is effectively condensed upwards until we reach the appropriate number of clusters. So you could have a huge hierarchy of vehicles organized down to the very nuts and bolts that are used to put them together. But then, if you only wanted 3 clusters, you condense the tree upwards from nuts and bolts, through make and model, and then upwards to just the type of vehicle: car, truck, or motorcycle. Then there's density-based clustering. Now, this is similar to centroid-based clustering, but it works on the density of clusters. Basically, it connects data points based on how many of them are in a given area. If an area of that data is more dense, then it's considered to be a cluster. Now, unlike centroid-based clustering, where the clusters are all the same size, density-based clustering can result in arbitrarily shaped distributions. Now, it also means that the data outliers remain unassigned because they don't fall into a particular cluster if they're too far away from the density cloud. Now, this can result in a more accurate set of logical groups, but it can be problematic when you have data that varies in density and has a higher number of dimensions. And finally, there's a distribution-based clustering. Now, put as simply as possible, distribution-based clustering groups data into clusters based on a particular form of distribution. And the most common would be a Gaussian distribution. Now, once data is organized into its various distribution buckets, let's say, then whether a data point belongs to one cluster or another becomes a method of calculating the probability that it belongs to that cluster. As a data point's distance from the center of a distribution bucket increases, the probability that it belongs to that cluster decreases. With machine learning, there's a couple of fundamental strategies involved in training a model. The most common strategy is what's called supervised machine learning. Now, we've talked about that a couple of times in this course already. But what is it exactly? Well, the main characteristic of supervised machine learning is that the models are trained using well-labeled data. In other words, the input dataset is well understood and the features are well described. In fact, generally speaking, supervised machine learning is usually synonymous with the idea that the training dataset already has the correct answer in it. Why? Well, when we're training a model, it's particularly handy to show the model what the correct answer should be. Then the model can be scored and improved upon to make sure that whatever algorithm it comes up with will match the expectation. For example, if you wanted to train a model to predict whether a patient is diabetic, you would use a training dataset that already included the answer. That way, the model can analyze all the features of the dataset and derive an algorithm that comes to the same conclusion. Now, there are lots of different types and implementations of supervised machine learning. For example, regression is probably one of the most common. Regression algorithms are about being able to estimate a continuous and therefore numeric output based on the input data. So, for example, if we wanted to predict the price of a car based on the characteristics of a car, that would be regression. Logistic regression is almost the inverse of regular regression. Put as simply as possible, logistic regression is about calculating the probability of a discrete output. So, for example, certain input data may result in any number of potential events. With logistic regression, we can determine the probability of each of those events based on that input data. Now, classification is another type of supervised machine learning. As we've talked about before, classification is about exploring the input data and assigning one or more classifications to that data. So in our example of determining whether a patient is diabetic, that's actually an example of supervised learning or a classification model. Another implementation of supervised machine learning is to use decision trees on the input data. Basically, all the input data is organized and sorted based on their features in such a way that the data leans towards our given answer. Then, in theory, if we get a new dataset, we can make the same decisions against that data that we did with our training dataset, and we can arrive at a logical conclusion. For example, we can say that the number of wheels on our vehicle is 2, but the weight is a bit heavier. Therefore, the vehicle is a motorcycle and not a bike. Now, support vector machines, or SVMs, are about applying all sorts of statistics to the input data and using those statistics to determine the likelihood of their impact on the correct answer in the input dataset. This helps us to identify weighting or importance on particular features in the dataset. Now, supervised machine learning is great because you can train your models based on some really well-articulated data, but it is difficult to do. The quality of your data is paramount. Garbage in, garbage out. You have to really work hard at making sure your data is as accurate as possible. If you use bad input training data, you're going to almost certainly cause yourself inaccuracies in your outputs. And don't think for an instant that the preparation of that data is easy. It's quite the opposite. It's not a matter of gathering data, putting it in a spreadsheet, handing it over to the data scientists. It's way harder than that. Every single individual piece of data should be evaluated for correctness. So you can imagine that this takes time and effort. Having a high-quality input dataset is time-consuming and expensive, but you get what you pay for, which actually leads to a pitfall I've seen many times: guessing. It's a lot of work to make high-quality data. You should get your SMEs involved in that process. If anyone looks at a value, throws their hands up, and guesses as to its validity, that can lead to problems. It means that you don't have confidence in that value. But remember, the model will assume that value is correct, meaning the model has confidence in that value. So if it's not correct, the model will have an inherent flaw built in. But while creating the needed input dataset is time-consuming, hard, and expensive, it's worth noting that there are tons of benefits to supervised machine learning. For example, all the data that you produce can be reused. The dataset is not a one-time use. You can apply it to all kinds of models. Some people even go so far as to making their datasets open to the world, so that other consumers can use that same dataset to build their own models. The most common example is weather data. Supervised machine learning solves real-world problems. You're using data you understand to make predictions based on past observations. So if we go back to our example of being able to predict whether a patient is diabetic, well, all of that effort that went into creating a valid input dataset can have dramatic, real-world benefits for years to come. And as the model grows, its experience and output can help to inform newer and better models. Its outputs can be inputs to other model runs. The resulting experience can lead to more and more optimizations of performance. But of course, there are drawbacks to supervised machine learning that we need to accept. First, as I already said, model training requires a lot of resources. We need to collect data, we need to organize, categorize, and label our data. We need to validate our data. We need to run the data through a model trainer, which means we need a lot of compute power. And we need to score and evaluate our model candidate. And then we need to tweak our parameters and do it all over again until we have something viable at the end. And this all takes time, money, people. And frankly, a model is only as good as the data that comes in. But a single data point is never going to be enough to train a model. So you need data, lots of data. And in reality, the more data you have, the better your model. And in lots of cases, the sheer size of data that you should feed into a model training exercise can actually present a real challenge to companies. And one more drawback is that relevant examples need to be chosen during training. So imagine a classification model. You need to already know what your classifications are going to be. For example, you need to know that you're looking for diabetes. You can't just say, "Here, Mr. Model, go make some sort of diagnosis." Supervised machine learning doesn't work that way. So if you're going to use supervised machine learning, there are a few best practices that you should follow. First and foremost, choose your dataset carefully. Remember, garbage in, garbage out. So your dataset needs to be the correct dataset for the operation that you want to perform. If you want to determine whether a patient is diabetic, you're not going to use a dataset from a dentist. And definitely leverage human expertise. SMEs, or domain experts, know what the data means. So they can help you to apply the correct labels to your data, as well as to tell you what the correct answer should be coming from your model. And finally, define the appropriate algorithmic structure for your dataset. We went over all the various types of algorithms out there, from linear regression to decision trees. Well, depending on what your input data looks like and what you want the output to be, you're going to need to choose an algorithm that matches your particular criteria. As I said earlier in the course, when it comes to machine learning, there's a couple of fundamental strategies involved in training a model. The most common strategy is what's called supervised machine learning. But after that, we have unsupervised machine learning. Now, we've talked about that a couple of times in this course already, but what is it actually? Well, the big difference between supervised and unsupervised machine learning is that unsupervised machine learning uses the raw data only. Now, unsupervised machine learning has no distinct or defined output variables. So why use unsupervised machine learning? If we know that supervised machine learning helps us to make predictions based on known answers from a training dataset, what use is unsupervised learning? Well, unsupervised machine learning is particularly handy when there are no specific answers that you're looking for. You don't know the answers that you're going to get are correct or even incorrect. They may be neither. They may just be additional insights. The point of unsupervised machine learning is that you don't have the answers, and you're not even sure what information you might be able to glean from the input dataset. Another way unsupervised machine learning is handy is if the goal is to model the structure of your data. Here, the intent is to create a model of your model. So to that end, there's no possible pre-existing answer. You're just trying to create the answer. Now, the other thing about unsupervised learning is that the algorithms that are implemented are effectively left to their own devices to discover an appropriate conclusion about the dataset. So let's look at some of the differences between supervised and unsupervised machine learning. First, the primary difference is that unsupervised machine learning uses raw data, while supervised machine learning uses labeled data. Now, technically, unsupervised machine learning can use labeled data, it just doesn't really pay attention to the labels. Next, unsupervised machine learning is computationally complex, while supervised machine learning is simpler, which makes sense, right? Unsupervised machine learning is about deriving some kind of meaning from the raw data, so naturally that's going to be more computationally complex, than a dataset that we fully understand, for which we know what the answer should be. And lastly, unsupervised machine learning is much less accurate than supervised machine learning. And again, that makes sense. With supervised machine learning, we train the model with the data that already has an answer, so naturally it's good at calculating that answer. Unsupervised machine learning doesn't have that luxury, so it's naturally less accurate. Alright, so now we understand what unsupervised machine learning is about, but why would we use it? What are some of the benefits of unsupervised machine learning? Well, one of the principal benefits of unsupervised machine learning is that the raw data that you're going to use in your model requires no upfront work. So it's way cheaper to create the datasets that you need for unsupervised machine learning. The benefit of unsupervised machine learning, or rather the primary use case for unsupervised machine learning, is that it can be used to detect unknown patterns. Now remember, we're looking to try to find some meaning in our data. So one thing that we're trying to do is identify new features for categorizations. For example, imagine I had a dataset of vehicles that I wanted to figure out some meaning to. I have no idea what to make of that data. Well, I'd use unsupervised machine learning to figure out what my possible categorizations could be. And that's where I might find that there are lots of useful categorizations, like type, color, or even engine size. Now, unsupervised machine learning can also be used to analyze any input data in real time. Now, when it comes to unsupervised machine learning, there are a couple of different types that are usually implemented. First, and probably most commonly, we have clustering. Clustering is about finding logical groupings of the data. Now, this helps us to categorize information. So if we go back to the example of my dataset of vehicles, I could use a clustering methodology to find out a logical grouping of my vehicles is type: motorcycles, cars, and trucks. But another type of unsupervised learning is called association. You've probably even encountered this yourself, even if you didn't realize it before. For example, a good association learning implementation would be for situations where you want to figure out what people tend to buy after buying certain other products. Now that would help you figure out what to offer customers after they buy certain things. So let's dig into clustering a little bit. There are actually a couple of different strategies when it comes to clustering. First, we have the exclusive strategy. An exclusive strategy often attempts to organize data into distinct clusters. Data points can only be in one cluster, and it must be in a cluster. Another strategy is what's called overlapping. Now with this strategy, there are still clusters of data, but with the overlapping strategy, a single data point may actually belong to multiple clusters. Next is the probabilistic strategy. In this case, data points are analyzed and their inclusion into clusters is based on the probability that they should belong to that cluster. And finally, there's the agglomerative strategy. With this strategy, every single data point is its own cluster and organized hierarchically. Then, depending on how many clusters you want as your answer, the appropriate level of this hierarchy is returned. Now let's dig into association a little bit. Now with association, the model attempts to create relationships between the various data objects in the dataset. The goal is to figure out how objects relate to each other. Now association is really handy for discovering new relationships between data. Sometimes you know that certain relationships must exist, but sometimes you're not quite sure what they are. So for example, imagine you wanted to sell some products to a new home buyer. Well, it'd be very useful to know what a new home buyer typically buys. So you might think obvious things like furniture or paint, but then after running the model, you're surprised to learn people buy pipe cleaning chemicals or filters for the fridge. So maybe you're thinking you want to use unsupervised machine learning. So here are a few use cases to look out for. One common use case is to subdivide or categorize a dataset based on similarities in that dataset. So again, we can use the clustering example of wanting to find logical groups for a giant dataset of vehicles. Another growing use case is detecting anomalies in a dataset. Now this is particularly handy in the process industry. Process data can be all over the map, but how do we know when an individual data point is worth looking into or taking action on? Is a spike really something to worry about? Now, data preprocessing is also a great use case. We can analyze a dataset and try to derive meaning from that dataset before feeding it into other models for processing. And finally, we get back to associations. Association mining is really handy for trying to discover the relationships that might exist in your data. Happy machine learning! So in this course, we've examined machine learning uses, data manipulation, and the difference between supervised and unsupervised machine learning models. We did this by exploring how machine learning is used, data and dataset manipulation, labeled, unlabeled data, and dataset use in AI algorithms, machine learning regression, classification, and clustering algorithms, and supervised and unsupervised machine learning models and their use. In our next course, we'll move on to examine how to describe the machine learning services provided by Azure.